Good evening, everyone. Welcome back. This is the next video in the Linear Algebra 1 series, and it's been a very, well, not a very, very long time, but quite a considerably long time since I've made the last part of this video, because one, I've been focusing on theory of computation series, and two, I've just had other things in my life, and posts on YouTube for me are not my top priority, given that it's not my job, and I have to focus on other big exams to my last year of secondary school in the UK. So there are things, requirements and things I need to prioritize. Other than this, but we're back. This is Linear Algebra number 1. And we are starting a new section. The new section is actually called Reduced Row Echelon Form. So we're going to go back and talk about linear systems in sort of a little bit more of a rigorous light. We're going to see today what we're really going to be sort of moving towards is a proof that effectively applying elementary row operations to a linear system keeps these solutions. So effectively, just as a reminder, the elementary row operations, effectively, one of them is to swap rows I and j. So if you have a linear system, right, you have the augmented matrix, and then you have basically a matrix of coefficients, that sort of vertical line, and then sort of the values that effectively are produced when you basically multiply that matrix of coefficients by, x1, the column vector x1, x2, all the way down to effectively xn. And so once you have that sort of augmented matrix, you can apply elementary row operations to it. So you can swap two rows, right? You can sort of multiply a row by some scalar constant lambda, which cannot be 0, otherwise you will be removing solutions. And you can add lambda times row I to row j. Okay? So, effectively, those are the rules that we have in terms of how I can sort of solve a linear system, right? Again, I already went over that in sort of some of the videos earlier on in the series. But today, we really are going to sort of prove a little bit more rigorously that and justify effectively the fact that applying elementary operations to a matrix leaves these solutions the same, effectively. So doesn't change the solution space, the set of solutions to the linear system. So effectively, we want to be proving the invariance of the solution space under the application of elementary row operations. Okay, right, let me just get onto the board here. I've also realized that I haven't really, let me make this, let me make the background dark so people can see that, okay? And then also going to add in vertical line here, vertical line over here. Okay, awesome. Actually, maybe because what I've kind of moved to doing now is just, in fact, I just do like sort of boxes now, but I don't know how good that is because it's not been the best in the past. But yeah, we'll see how it goes for this video anyway. Okay, so here we go. And it's a new section. Okay, so this is section 1.3, and it's called Reduced Row Echelon Form. So Reduced Row Echelon Form. We're not actually going to talk about Reduced Row Echelon Form today, but one of the things that we'll prove later is that effectively every linear system can effectively be transformed into this special format, which we call Reduced Row Echelon Form, where you can effectively just, at that point, once you've transformed it into that format, you can just read off the solutions, basically, or tell if there are 0 or infinitely many. So that's going to be useful for us, and we'll prove that in a later video, probably the next one, actually, or if not the one after that, depending on how dense, sort of the theory is. But ultimately, today, we're literally not going to be talking about that. We're going to be talking specifically about EROs, so elementary row operations. Obviously, we've already introduced them in previous videos, but now we're going to sort of bring them back, and we're going to sort of talk about them as something called elementary matrices, which effectively are just the matrix format of elementary row operations. So let's just sort of, let's just get straight into this. Okay, so we're going to start off with a theorem. There are pretty much two main theorems and a corollary, which I want to look at today. And that's pretty much it. But they're quite dense. So the first theorem is as follows. Basically says, if I give you a matrix A, which is an m by n matrix, so just any standard matrix, right? So m rows and n columns, m by n matrix, right? Then effectively what this theorem says is that applying any of the EROs that we're familiar with. So if you're not familiar with the EROs, especially the notation that I've been using so far, please do go back and look at the video. It was one of the first ones in the series. We spoke about linear systems. So applying any one of the EROs, and the EROs that we used and previously were Sij, so you're swapping row I with row j, and that's effectively what that was doing. And then you also have mi and then lambda. So if you need to give me an input lambda and also specify which row you're talking about, so that I can basically multiply that row of your augmented matrix by the scalar constant lambda, which is not equal to 0. Okay, so that's that elementary row operation. Well, these should all be familiar. So if you're not familiar with what I'm talking about, please go back and watch the previous videos. And lastly, we have the sort of capital Aij of lambda. So that's the final elementary row operation, which basically just adds lambda times row I to row j. So you have a matrix, you have rows I and j, respectively, and effectively, where I is not equal to j, because otherwise you're just adding the same row to itself, and you can just use mi of lambda instead. But effectively, you just have a matrix, your augmented matrix, two separate rows I and j, and you're multiplying row I by lambda, so every single time in row I you multiply by lambda, and you add it to row j. That's all that elementary operation is doing. So what this theorem is saying is that applying any of these EROs is equivalent actually to pre-multiplying. So is equivalent to pre-multiplying. So if you don't remember that, we spoke about that a couple of videos ago. So obviously matrix multiplication is not commutative. So matrix A multiplied matrix B is not the same as matrix B multiplied matrix A. So you have to specify whether you're multiplying pre-multiplying or post-multiplying. In other words, multiplying on the left or the right. And in this sense, pre-multiplying means multiplying on the left. Okay, so applying any of the EROs to your augmented matrix is the same, is equivalent to pre-multiplying effectively A by, so this matrix A by certain matrices, which we also denote as Sij, Mi lambda, Mi of lambda, and Aij of lambda, respectively. Yeah. Okay. So ultimately, I mean, even if you don't have an augmented matrix, it still makes sense to talk about these elementary operations, right? So if I just give you a matrix A, right? Although obviously this will be applied to linear systems, so we'll be dealing with augmented matrices. But if I just give you a matrix A and I want to swap rows I and J, effectively we can talk about that elementary operation. We can apply it physically because we can just swap them manually, or we can actually pre-multiply, and we'll show this. We can pre-multiply that matrix A by another matrix, which effectively represents the row operation Sij. So ultimately, we have these matrices that represent the elementary row operations. So obviously, you understand what I mean when I tell you multiply this row by 3, for example. But in other words, what this is saying is that there's a matrix that basically does that for you. So once you pre-multiply a matrix A by that matrix, it will effectively do the same thing. It will multiply the row that you want to multiply by 3. As long as you design it correctly and engineer it correctly, you'll be fine. That's basically the whole point of this. Okay, so specifically, we obviously need to outline these matrices. So specifically, these matrices have entries. Okay, and then we need to specify. So the ijth entry of capital S, lowercase capital I, capital S, capital subscript, capital I, capital J. So this is a matrix, right, which represents effectively me swapping rows I and J. Well, it represents it once I pre-multiply my matrix A by it. So it's a matrix and it's defined sort of quite confusingly, but effectively it's defined as, so there's a 1 in each position where lowercase I is equal to lowercase j, but they cannot share the value of capital I or capital J. Okay, so basically what this is saying is that if I give you a matrix, obviously when lowercase I is equal to lowercase j, that just represents the diagonal of your matrix. Okay, and effectively what this is saying is that there's going to be 1s along the diagonal, except for in the positions capital I, and capital J, respectively. Okay, so in those positions there will not be necessarily a 1. Okay, we haven't finished it yet, but there actually won't be a 1 in those positions. There'll be a 0. Okay, so effectively what this is saying is that we're constructing a specific matrix with 1s along the diagonal, with 0s in those 2 specific positions. Okay, fine. And then also we have a 1 specifically in this position where I is equal to capital J and lowercase j is equal to capital I. We'll also have a 1 in position where lowercase I is equal to capital I and lowercase j is equal to capital J, and then we'll have 0s otherwise, right, or elsewhere. So this is just a specific matrix which effectively has 1s along the diagonals except for in those 2 positions. It will also have a 1 in the position J, capital I, and it will have a 1 in the position capital I, capital J. Okay, obviously I need to specify what capital I and capital J are, right? And I also need to specify, the dimension, or at least m. So I need to specify the number of rows of my matrix A. Okay, so an actual a physical example of this is effectively when A is equal to 3, right? Sorry, when m is equal to 3. So when m is equal to 3, right? Then obviously the matrix capital A has, basically 3 rows and n columns. Doesn't matter how many effective columns it has. But what we know is that, by applying any elementary row operators to matrix A, I need to keep its dimensions the same, right? Because all I'm doing is I'm swapping 2 rows or adding or multiplying a row by some scalar or adding some multiple of a row to another row. I'm not actually changing the dimension of the matrix. I'm not changing the dimension of my augmented matrix, and I shouldn't be changing the dimension of anything. I'm just changing the values inside the matrix, which means that all of these matrices that I'm pre-multiplying A by, first of all, they have to commute with it. So effectively the number of columns has to be the same as m, which is 3. But also the dimensions of the matrix that's produced needs to be also 3 by n. So actually, all of my elementary row operations, when m is equal to 3, have to be, if they're represented as a matrix, of it sort of have this dimension, which is 3 by 3. So they have to be a square matrix, okay, of basically m by m matrix, right? So an m by m square matrix. That's in this case I specified m is equal to 3. So all of the matrix forms of my elementary operations have to be effectively 3 by 3 in this case, right? Even though I might not necessarily know what they look like, I know just by intuiting what they're going to do that obviously the dimension has to remain the same of A after applying them, after pre-multiplying them, the dimension has to stay the same. And also, obviously, because you're multiplying matrices, you want them to commute, so you need to have, obviously, the number of columns in any of your elementary operations to be the same as the number of rows in the matrix A. So obviously, in this case, we have this, and obviously, and in this case, obviously, capital Sij will always be 3 by 3, okay? An example might be in this specific case or S21. Okay, so in this case, right, it's going to be a 3 by 3, and by the rules here, we're saying that there's going to be ones along the diagonal, except in the position. So in this case, capital I is 2, and capital J is 1. So there's not going to be any 1 in the position 1 1, no 1 in the position 2 2, and there will be a 1 in the position 3 3. So there's going to be a 1 over here and zeros elsewhere on the diagonal. And then also you're going to have a 1 in the specific position ji, which is just 1, 2. So you're going to have a 1 here, and you'll also have a 1 in the position ij. So that's going to be 2, 1, which is here, right? And then you're going to have zeros elsewhere, okay? So, yeah, okay? This is effectively the elementary row operation, which once you pre-multiply any matrix A, any 3 by n matrix A by this matrix, you will basically swap the rows of the sort of first and second row of A, okay? And I'm pretty sure that actually this will be the same as well, obviously, as S12, because you're doing the same thing, right? So you don't need to have a different matrix, and I think by design they'll actually end up being the same. Because yeah, you'll have zeros in the diagonal except for 3 3. You'll have and it just swaps. So I and j swap, so you'll have the same matrix, and that makes sense because when you're pre-multiplying any matrix A by this S12 or S21, you're doing the same thing. You're swapping two rows, okay? And another important thing to note, which we'll talk about as well, is that this is very similar to the identity matrix. Okay, in fact, it is the identity matrix, but actually with the elementary operation performed on it. So actually, it's the identity matrix with the first and second rows swapped, right? So, and that's on purpose. That will always be true. In fact, Sij will always be m by m. Okay, if A is capital A is m by n, and it will always be the identity matrix with rows capital I and capital J swapped, always. Okay, and it's sort of by design, really. Okay, so you can sort of investigate that yourself, but that's always going to be true. Okay, and so yeah, that's that. So that's the first elementary row operation matrix, effectively. So now we need to talk about the second one. Okay, here we go. Okay. Right, so next, we want to talk about the ijth entry. So the ijth entry of the elementary row operation matrix, which effectively multiplies row I by some scalar lambda, which is not zero, non-zero. So effectively, this is just a matrix, and we define this matrix as follows. It's a little bit easier to understand. So you have ones, effectively, in the diagonal, this is what this means, except for in the position capital I, okay? And in that position capital I, you will introduce a lambda, which is obviously of your own choosing, okay? And then zero otherwise. Okay, so this is effectively the exact same, actually, as the identity matrix, but instead of having a 1 in the position capital I, you'll have a lambda, okay? That's pretty much it. So, for example, in the case where m is equal to 3, obviously this also has to be 3 by 3 by the same argument that we used before. The dimension of capital M lowercase subscript capital I of lambda has to be 3 by 3, it has to be 3 by 3, okay? And it's going to be a 3 by 3 identity matrix with lambda in the position capital I, which we haven't specified yet. So, in this case, capital M subscript 3 of 7, okay, it's going to be a 3 by 3 matrix with the with lambda, which in this case is 7, in the position 3 3, and then just 1. So the rest is just a normal identity matrix, right? So effectively, capital M subscript 3 of 7, in the case where lowercase m is equal to 3, is going to exactly look like the identity matrix, but instead of having a 1 in the position 3 3, you'll have lambda, so through a 7 in this case, right? So it looks like this, and effectively, what this is going to do is when you multiply this matrix by any 3 by n matrix A, effectively what you're going to be doing is you're going to be scaling up the third row of A by a factor of 7. So multiplying each of the entries in the third row of capital A by 7. Okay, so that's basically the matrix form of the elementary row operation that will multiply row capital I by some scalar lambda. That's obviously non-zero. And lastly, we obviously have the we need to talk about aij of lambda. Okay, so the ijth entry of the matrix that represents that row operation. So capital A, lowercase capital I, not subscript capital I, capital J of lambda is effectively just going to be a matrix. In this case, it's literally going to have ones along the diagonal, so just literally all ones along the diagonal, no exceptions. But instead, this time we'll have a lambda specifically in this position, in the position capital J, capital I. Okay, so that's it, and zeros otherwise. Okay, so that's pretty simple to understand. Pretty much an identity matrix again, but with a lambda in the position J, capital I. Okay, so that's the matrix form of this elementary operation, which basically adds lambda times row capital I to row capital J. Okay, and again, we can go through the example of this. Okay, so again, going with m is equal to 3, just why not? If we wanted to represent this elementary operation here, so you're adding -2 times row 3 to row 1 of capital A, then that matrix would obviously have ones along the diagonal, and it would have a -2 in the position 3, in the position, sorry, 1 3, because it's in the position J, capital I, and in this case, capital J is 1, and capital I is 3. So you want to look at 1 3, so the first row in the third column, you're going to have a -2 in that position, then the rest is just an identity matrix setup. Okay, so basically that is this matrix, and effectively what it does is when you pre-multiply any matrix capital A, which is of the form which has dimensions 3 by n, by this matrix, effectively what you're doing is you're going to be adding -2 times row 3 to the first row. Okay, so that's that. well, I mean, we still sort of need to sort of talk about that a little bit more, but those are the entries of each of the elementary row operation matrices, okay? And we call these matrices the elementary matrices, okay? So the above matrices are known as the elementary matrices, are known as the elementary matrices. And again, alluding to the identity matrix, okay, each of these matrices is basically just the identity matrix, but with the specific row operation performed on it. That's how you can find them pretty easily, right? So obviously you need to know what lowercase m is, but once you know that, you just need a square matrix, and you just, first of all, you can construct any of these by taking the square m by m identity matrix, and then performing actually the row operation that you want on the matrix form of on the identity matrix, right? So for example, for lowercase m equals 3, I have a 3 by 3 matrix. I have 3 by 3 identity matrix, right? And then I perform this operation on it, which is basically just multiplying the third row by 7, and that gives me this exact matrix, right? And that's not a coincidence. That is pretty much by design, okay? And that will always be true. Same thing here, right? So basically, in this case, what we're doing is we're adding minus 3 times row 3 to row 1. So you take the 3 by 3 identity matrix, and you add minus 3 times row 3, so that's 0, 0, minus 3 to 1, 0, 0. Sorry, minus 2 times row 3 to row 1. So you multiply row 3 by minus 2, that gives you 0, 0, minus 2, and you add it to effectively 1, 0, 0, right? So 0 plus 1 is 1, 0 plus 0 is 0, and minus 2 plus 0 is minus 2. So you're going to have 1, 0, minus 2, 0, 1, 0, 0, 0, 1, which is exactly the matrix that we have here. So it is a true fact that you can actually construct all of these matrices, okay, which are elementary row operation matrix equivalents, using this identity matrix procedure. So by taking the m by m identity matrix, you need to look at what lowercase m is, and then performing the given row operation on the identity matrix, okay, that you care about, that you want. Okay, so that's how you can find it like pretty quickly without having to worry about the semantics and even memorizing them. You don't even need to memorize them actually. You don't need to memorize any of this detail about 1 lambda 0, 1 lambda 0, any of that. You need to memorize any of that. You need to know, well, you need to understand it, but you need to know, all you need to know in practice is just that you can effectively take the identity matrix and perform this elementary row operation on it, right? Which makes sense because obviously if this is going to be effectively a matrix that scales up any 3 by n matrix, right, by the third row of it by 7, well then a specific example of that 3 by n matrix would be the identity matrix, right? So it also needs to work for the identity matrix, right? It needs to do the same thing for all 3 by n matrices, which include within them the identity matrix. So it's sort of a nice hack. I don't know, that's probably not the right word, but it's a nice trick, okay, that you can use. Sorry, my Siri just turned on. Okay, right. And effectively, I mean, we can sort of go ahead and sort of prove this in a sense, although the sort of proof that I have sort of prepared is sort of not necessarily a particularly rigorous proof. I'm sure that there's a way that you could probably incorporate the stuff we've already learned in terms of, because in the notes it does say left as an exercise. So the proof that I've sort of incorporated is not necessarily the most rigorous. It's more of sort of an explanation, which has pretty much already been given here, as to why this theorem is true, right? Because what the theorem is saying, we obviously clouded what's going on. Basically, all this is saying is that I have these matrices which represent elementary row operations, and if I pre-multiply any matrix A by them, I'm effectively just performing the elementary row operations. That's all it's saying. And in a sense, I'm sure there's a proof that probably makes use of the matrix multiplication sort of definition that we've utilized, that we learned in previous videos and things like that. But I'm just going to go through a proof that sort of just talks about it and sort of gives it sort of a good intuition as to why, but not necessarily sort of goes through those definitions and sort of the matrix multiplication stuff. I might do that in a later video if I find a proof that is of that form. But for now, we'll just deal with this. We'll just do it this way. So here's sort of a pseudo proof, if you will. So first of all, we need to talk about why this works we'll talk about it for each of the individual elementary operations. And the first one is obviously the one that swaps row I and j. And I think this is the most complicated one, actually. So the first thing that we notice, right, that I've already mentioned, is that notice that effectively this matrix, capital S subscript capital I capital J, is actually just the m by m identity matrix, right? Because it has to always be m by m. If I give you lowercase m, you can specify it, right? But with the ith row swapped to the jth row, right? But with the ith row swapped with the jth row. And yeah. And it would make sense, right? I mean, if there is any matrix that is going to do as we would like it to do, then it needs to also do as we would like it to do to the identity matrix, right? Because that's just an example of an m by n, right? And obviously this always has to be of the form m by m. So, just take the identity matrix, and then it's pretty easy to construct the elementary row operation that will do what you want, because effectively it has to do it to the identity matrix, right? So you basically just think, okay, if I perform this on the identity matrix, I'll just get the elementary row operation matrix back. Okay, so I can actually construct it pretty easily by just taking the m by m identity matrix and being like, okay, if I want the elementary row operation matrix that scales up, let's say row 3 by a factor of 3, just multiply row 3 by a factor of 3, and that will give it to me, right? And so effectively, that's how you can construct them, and that's effectively what we're doing with all of these. Actually, in this case we're just swapping row 1 with row 2 to get this matrix that will always swap the first and second row of a 3 by n matrix. Okay, in this case we're just multiplying row 3 by a factor of 7 in the identity matrix, and we've already gone through each of the examples. It's effectively all that this is, all that these matrices are. They're just the identity matrix, but with the elementary operations performed on them. Okay, yeah. Okay, so what I wrote in my notes is already what I basically explained. And so if I can go down here, okay, didn't mean to do that. Sorry, a bit of OCD here. Just want to get that right. Okay. So hence, obviously, since this is true, okay, hence, effectively the ith row of the matrix multiplication of S, the sort of elementary operation that represents the swapping elementary operation matrix that represents the swapping of rows I and J. Effectively, the ith row of that matrix multiplies, so obviously matrix A pre-multiplied by that matrix. The ith row of that resultant matrix that I get from that matrix multiplication is actually just going to be the jth row of A. Okay, and similarly, right, and the jth row of sort of that matrix multiplication, the resultant matrix that I make when I multiply those two matrices, is just going to be the ith row of capital A. Okay, and the reason for this is fairly simple, right? We're basically just taking the identity matrix, but with the sort of capital ith row swapped with the capital jth row, and we're applying it to capital A, which is just some arbitrary 3 by n identity matrix. And so effectively, what's going to happen, right, is let's just take a specific example when I have m equals 3 and s 2 1 that we've already looked at before, right? Just to really make this concrete. So if we have 0 1 0, 0, sorry, was it 1 0 0? I think it was. Yeah, 1 0 0 0 0 0 1. Right, when I take this matrix, right, suppose that I'm just pre-multiplying some matrix A, which is 3 by n. Let's say it's 3 by 3, just for the sake of argument. Okay, what's actually in the matrix doesn't matter, but you can see that what's going to happen is effectively, let's say that I take the, in this case, what was capital I? Capital I was 2, right? So in this case, if I take, effectively the jth row, right, of capital, so in this case, sorry, so once I multiply effectively this first row by, so when I'm multiplying this matrix, what I do, right, is effectively I dot each row with each column of effectively the matrix capital A. So, as an example, right, with this first row here, what we're going to do is we're going to sort of dot that with each of the individual columns of capital A. So if we do that, what we're going to get is obviously 0 times A, so that's 0, plus 1 times D, that's D, plus 0 times G, that's 0, right? And obviously what you can see is that because of the fact that the 1 is placed here, the only row that's ever going to come out of that sort of multiplication is the second row, right? Because, so whenever I dot this with all of the columns of matrix capital A, I'm only ever going to get this row, right, as the resultant. So what I know, therefore, is that effectively, this is row J in this case, so effectively, I know that the ith row, or which row would it be? I know that this would be so you're doing the first row dotted with the first column, so that's position 1, 1, so that's going to be D, that's going to be E, that's going to be F, right? So I know that the first row, effectively, of the resultant matrix, right, which in this case 1 we know is J, so effectively the first row, so row 1, in this case because capital I is just 1, so the first row of this resultant sort of matrix that I get when I multiply those two matrices together is simply just going to be the second row of A, right? And similarly, the second row, right, is just going to be the first row of A, right? Because in this case, we just swap those two rows in the identity matrix. Whenever I dot this individual row with each of the columns here, all I'm going to be doing, all that's ever going to come out of it is this first row, right? Because everything else is going to be multiplied by 0, so it just crushes everything else. And so actually, all that I'm going to get is this, right? I'm just going to get, D, E, F. So I'm going to get A, B, C being here, right? And then the last row will just be G, H, I, right? Because you're going to do 0, so the only thing that will ever come out of that is this row, right? Because everything else will be multiplied by 0, right? So just to recap, effectively what I'm doing is, whenever I'm doing a matrix multiplication, I'm dotting the ith row, right, with sort of each of the columns. I'm dotting each row with each of the columns of matrix A. So effectively, I'm dotting each row of this elementary operation matrix with each column in capital A, right? So, for example, I take the first row, and to get the element that's in the first in the position 1 1 of my new matrix, I dot this with the first column. To get the element in position 1 2, I obviously dot this row here with the second column here. So that's going to be 0 times D plus 1 times E plus 0 times H, and hence E is in this position 1 2, right? And so on and so forth. But all I'm really doing is, and all I'm going to do when I multiply matrices is I'm going to take each row and I'm going to dot it with each column of each row in sort of the matrix to the left. So in this case, that's just the elementary row operation matrix, and I'm simply going to dot it with each of the columns of capital A. Okay, and so you can see that because of the fact that there's only that we've swapped these two rows, that's effectively going to have the same sort of that's effectively going to swap these two rows for any 3 by n matrix that I take. In this case, I've chosen n to be 3, right? And the reason for that is just because effectively all we're doing is we're dotting each row of capital S subscript I, capital J. We're dotting each of these rows with each of the columns of capital A. Okay, and in doing that, because when the 1 is placed second, doing that is only ever going to give you the second row, because everything else will be multiplied by 0. So for example, if I want to find the element in position 1 1 of my resultant matrix, all I would do is effectively 0 1 0 dotted with A, D, G, right? And so I shouldn't really put commas there. And so all that's going to do is going to do 0 times A, add 1 times D, add 0 times G, right? And that just gives me D. And no matter what, right? 0, 1, 0 dotted with any column vector will just give you the second component, right? Because everything else will be multiplied by 0. And so you can see that actually the first row, but this is going to be in the first row of my resultant matrix. And so actually this is the same effect as swapping those two rows. Sorry, I know that wasn't the best explanation because it's a little bit, when you get into semantics, a little bit confusing. I didn't want to make a mistake. But effectively, this is, you can see here that this is doing the same thing, at least in this case, as just swapping those two rows, which is exactly what we want it to do. And in general, it's doing that because all you're doing is dotting each row of your elementary row operation matrix with the matrix, of your choice, capital A. And what that's going to do, because you swap two rows of the identity matrix, is that's effectively going to have the same effect as swapping the two rows in capital A, right? Because when you, if you just take the identity matrix and you multiply it by any other matrix, you're just going to get the same matrix back. If you swap two rows of that, effectively the effect that's going to have is it's now going to put zeros where it initially put ones, and then ones in sort of the ones in the row of your choice that you want to swap effectively. So effectively, if I had just a typical identity matrix 1 0 0 0 1 0 0 0 1, and I had this 3 by 3 A B C D E F G H I, right? When I do this, obviously I'm just going to get this matrix back. This is something we looked at in a previous video, right? But when I swap these two rows, what I'm going to be doing is equivalently swapping these two rows, because now, although when I used to do my dot product, I used to have ones that would correspond to me getting the first row of my resultant matrix being the same as the first row of capital A. But in this case, when I swap it, now I'm going to have a 0 instead, which is effectively going to have the same effect as now crushing that first row and actually giving me that second row where my first row used to be. Okay, quite tricky. But the concept should be is to be fairly simple, right? Of what you're doing. And this is just me trying to give an intuitive explanation based off of what we've already seen. Okay, so yeah, and obviously all other rows, other than effectively the two rows that you wish to swap, will be unchanged because the identity matrix hasn't changed there, right? So you're just going to be doing the same thing as you were doing previously in terms of dotting that row with all the other rows, columns in A, right? So effectively that that nothing else will change. So the only two differences that are going to be made is specifically these two differences here. Okay, so the ith row of your resultant matrix will be the jth row of A, and the jth row of your resultant matrix will be the ith row of A. Okay, and all other rows are unchanged. Okay, right, and so thus, right, clearly we can see that S capital subscript capital I capital J multiplied by A, the matrix A, is simply just A, but with the ith and jth rows swapped. So I should say capital I. Okay, so the second example, which is I think a little bit easier, is the elementary matrix. So we have the other elementary matrices. The second one is the one which effectively has the same effect when you pre-multiply matrix A by it as multiplying any of the rows by some non-zero scalar lambda. So the elementary matrix, capital M lowercase, subscript capital I of lambda is effectively, again, this is something that I was noticing that I noted before. It's just the identity matrix IM is just effectively, let me just write, it's just IM. So the M by M identity matrix, right, with lambda added in at sort of the position capital I, right? That's all that I've done, okay? And the effect of this, like the tangible effect of this is just, there's only one real big effect here, and that's that the ith row of the resultant matrix that you get when you multiply that elementary row matrix by effectively matrix A, the ith row of that is going to be lambda times the ith row of A, right? And that's exactly what you want, right? Because you want the ith row of sort of A to be scaled up by lambda. So that's effectively what's happening here. Okay, and again, this is a fairly, not too tricky to see because all I'm going to have is just 1, 1, 1, 1, and then have some lambda. Okay, I mean, let's have a look at the example that we already had before. So if we have m3, so lowercase m is equal to 3, then m subscript 3 of 7 is just going to be effectively this identity matrix with 7 and 3, 3. So 1, 0, 0, 0, 1, 0, 0, 0, 7, okay? So when lowercase m is equal to 3, and this is effectively that matrix that when you multiply it by capital A will effectively scale up the third row by a factor of 7. And the reason for this is fairly simple, right? Because effectively, if I just were to take let's take a 3 by n, we'll choose n to be 3, just for the sake of example here. So this is my matrix capital A, right? All I'm doing again is I'm dotting each of these rows with each of the columns in capital A, right? And so effectively, obviously doing this, so 1, 0, 0 dotted with each of the column vectors will just give you the first element of that vector, which is just going to be this row effectively. So the first row will remain unchanged, right? Just be A, B, C. Same with the second row, so you're going to get D, E, F. Then the third row, instead of a 1 here, you have a 7. So it's going to give you 7 times the third element, or effectively these. So 7 times each of the elements in the third sort of position, each of the third components of your column vectors, right? Because effectively 0, 0, 7 dotted with any column vector ABC is just going to be 7C. right? Because 0 times A plus 0 times B plus 7 times C is 7C. Okay, so all you're ever going to be doing is taking the third component of each column vector and multiplying it by 7 to get the resultant. And so that means that in your new matrix, you're going to have 7G, 7H, and 7I, which is effectively done exactly what you wanted. It's kept everything the same, but multiplied row I by a factor, or row capital I by a factor of lambda. Okay, so you can see why the above is true. So the ith row of the resultant matrix that you get when you multiply the elementary row matrix, that represents effectively multiplying the ith row of capital A by lambda, and once you pre-multiply capital A by that, the resultant matrix that you get, the ith row of that is simply going to be the lambda times the ith row of capital A, which is exactly as you wanted. Okay, so and you can see there why, right? And that argument extends, right? Because it's all like the multiplication of matrices is always the same. It's always just that dot product, and so it'll always give you the same sort of output, right? For all of the elementary matrices, capital M subscript I of lambda that exist, right? Okay, fine. And so effectively, so capital M subscript I of lambda multiplied by A is just A with row I scaled by lambda. Okay, and then the last example that we need to look at is the elementary matrix capital A subscript ij of lambda. So the elementary matrix capital A subscript capital I capital J of lambda, right, is, again, this is just what we've been noticing the whole time, is just the m by m identity matrix with an extra lambda in position capital J capital I. Okay, and again, we're going to notice exactly what you would expect, which is that you're going to notice exactly what you'd expect. Sorry, my throat's drying up a little bit. Which is that effectively, hence, the jth row of the resultant matrix that you get, so capital A subscript capital I capital J of lambda multiplied by capital A, is actually going to be the jth row of A, right? Basically, add lambda times the ith row of A, right? Okay? And again, this is exactly what you want, right? You're literally doing this. The whole point of this elementary operation is you're adding lambda times row I to row J, and that's exactly what's happening, right? And then you're changing row J accordingly. So the new row J is going to be the old row J plus lambda times row I, which is exactly what you wanted, right? So this makes sense why this is true, and at least it makes sense, it makes sense why it's true. And a similar process in terms of the the dot product will get you sort of the intuition as well behind that, right? Because what you're already doing here, you have this matrix A3, 1, and minus 2. So what's that? For lowercase m is equal to 3, it was 1, 0, minus 2, 0, 1, 0, 0, 0, 1. Okay, so this is what it looks like. Obviously, whenever let's just choose a 3 by 3 matrix, just to keep things simple here. So you dot each row with each column with a 3 by 3 or capital A, right? And obviously these are just going to remain the same. It's just a normal identity matrix. So the second and third rows are going to be the same with the resultant. That's just going to give you D, E, F, G, H, I. And in this case, what you're going to be doing actually is, in this case, a bit more complicated, right? So you're going to have one copy of the first component of each column vector, add minus 2 copies of the third component of each column vector, right? Because effectively that's what this is doing, right? When you do that dot product, you're going to get this, which effectively gives you just A plus 0D, so that's just 0, minus 2G, so plus minus 2G, which is just A minus 2G. And that's always true for each of the components here. So your first row will simply be A minus 2G, currently write the entire row here, but it'll effectively be A minus 2G, B minus 2H, and C minus 2I, which is exactly what you want. You want the first row, effectively, well, in that specific case, what was capital I and capital J? It should be 3, 1. So exactly, you want to add minus 2 times the third row to the first row, and that's what you've done. Because the resultant matrix is going to be now A minus 2G, B minus 2H, and C minus 2I. You've done exactly that, right? You've added minus 2 times the third row, which is GHI, to ABC. So that's D, E, F, and GHI. And that's exactly given you, and that's really the intuition for it, right? That dot product is basically telling you exactly what's happening. So there we go, right? And all of the rows are obviously unchanged, right? Because it's just a normal identity matrix. And other rows are unchanged, right? Thus, capital A subscript capital I capital J of lambda is just the matrix capital A with the ith row replaced by effectively that linear combination. So the jth row, do I mean the ith row actually? Sorry, I think I mean the jth row is replaced by that linear combination, sorry. And it should put capital J on. With the capital jth row replaced by that linear combination. Yeah. Right, because you're adding lambda times row I to row J, so you're basically just changing row J. Right? And the linear combination we're talking about is just adding lambda times row I to row J, so just this, effectively. Okay? Okay, so that's actually the entire proof. We already looked at those examples. And so now what we need to show the second thing we need to show out of three is that actually these matrices are all invertible. Okay, so now we know what elementary matrices are. They're basically just matrices that represent effectively our elementary operations, right? In other words, when you pre-multiply a matrix capital A by these matrices, you're going to get the effectively matrix A transformed by the specific row operation that you're considering. Okay, so we now know what they are, but we now need to show actually that they're invertible, so that they have an inverse. Okay, and although it might sound a little bit tricky, actually, you can intuit it again quite easily. So, theorem. Okay, here's the next theorem, and it's that the elementary row operations are invertible. Okay, so that's the theorem that we're considering here. I won't do that. Let me just do something like this. Okay. Right. So here's a sort of proof. It's not really, again, it's sort of a pseudo proof, but I think it's suitable, right? I think it's fair enough because it really just gives you the intuition, and that's kind of what you need. But again, later on I might come back to these and maybe provide some more rigorous proofs if I can find any, or if I can think of any. Right. So let's talk about, first of all, let's go through them one by one again. Okay. So we'll start by talking about the capital S subscript capital I capital J matrix. Okay. So first things first, let's start with number one. So note that capital S subscript capital I capital J multiplied by the matrix capital A, what it does, right, and what we've basically shown it does in the previous sort of discussion, is that it swaps rows I capital J in matrix A. Right? Now I'm going to call this new resultant matrix, I'm going to call it B, okay? The new matrix B. Right? And I'm going to effectively multiply that, pre-multiply this new matrix B by capital S subscript capital I capital J. Okay? So, and note that capital S subscript capital I capital J so multiplied by the matrix B is obviously going to be the same, first of all, as multiplying capital S subscript capital J capital I by matrix B by that matrix, right? Because effectively those two matrices are the same. Capital S subscript capital I capital J and capital S subscript capital J capital I are the same, right? And you can kind of see that also by the way that we constructed it, right? Because obviously none of this is going to change. It's going to have ones in the same positions, right? At least it's going to have ones on the diagonal except in capital I and capital J, and they stay the same, just swapped. Okay, and obviously the one that was in capital J capital I, right, because you swapped those two around, it's effectively, you know, it was already covered, right, because you had a one initially in capital I capital J, and now your new capital I is your old capital J, and your new capital J is your old capital I. So actually, now your capital I capital J will effectively be your old capital J capital I. So you're just swapping the position of these two ones, right? So you're keeping all of the ones in the longer diagonal the same, and you're just basically swapping those two, the second and the third, right? Hopefully that makes sense. I know that wasn't the best explanation. But effectively, I'm going from capital I capital J, right, as in my new capital I. So if I were to consider by definition S capital J capital I, well, that would just be the same, right? Instead, it would just be having ones along the diagonal, except for in obviously capital J or capital I. That's the same, right? Just you swap capital I and capital J, right? So it still has the ones on the diagonal in the same position, right? It has a one in capital lowercase I is equal to capital I, lowercase j is equal to capital J, right? Which is actually just taking the initial third row, right? Because that's the same thing as what we had here, and I've now moved it to the second, right? Because my new capital J is my old capital I. But then I'm going to compensate for that by having effectively the third row being my old second row. So actually here I'm going to have the one. I'm going to have I in capital J. So I'm going to have one in the position capital J capital I, right? And then zero otherwise. Okay, so this is actually the same matrix, right? By construction, and also you can also obviously intuit it, right? Obviously you're doing the same thing, so there's no need for any other matrix, right? You're swapping the first, second row in both cases. Okay, swapping the first and second row is the same as swapping the second and first row. So first of all, we know that those two things are the same. Okay, right? And what does it actually do? Well, and that obviously we've shown from the previous discussion that swaps rows I and J in matrix capital B. Right? Which basically brings us back to matrix A, right? So that's bringing us back to matrix A. So we've just reversed what we've done, right? We swapped the two rows, right, and then swapped them right back, right? Even though we defined a new matrix, we just basically swapped once and swapped twice, and that gave us the initial matrix we started off with, right? So obviously it's clear, therefore, that S capital IJ multiplied by matrix B is just matrix A, and that obviously implies that capital S capital lowercase capital I subscript capital I capital J multiplied by S subscript capital I capital J multiplied by A is simply just the identity matrix multiplied by A, which is just A, right? Because we know that this gives us A, right? This is the same thing as capital S subscript capital I capital J multiplied by B. This is just effectively the same because we define B as capital S subscript capital I capital J multiplied by A. So this is the same thing as S capital S subscript capital I capital J multiplied by B. It's the same thing, right? And obviously we know this gives us A, and A is the same as IA. So effectively this chain of reasoning is correct. And so you can actually see that this capital S subscript capital I capital J multiplied by capital S subscript capital I capital J will just give us the identity matrix. Okay, it has to, otherwise you wouldn't be able to get A back, right? Okay, and it follows. Right, and it follows that the inverse of swapping, row I with row j is effectively just swapping row j with row I, or just swapping row I with row j again, right? So once I've and that's that's also true for the matrix capital S capital I capital J. The inverse of that matrix is just itself actually, pretty much, okay, which is pretty interesting. And it makes sense because when you swap rows I and row I with row j, just swapping the same pair again is just going to give you back what you started off with. So that makes sense, right? Okay, now let's look at the other matrices and show that they're invertible. But it's a similar idea. It's just reversing what you've already done, basically. Intuitively, obviously, that's going to give you what you started off with, and then you can show that gives you. Then you can use that to find the inverse, right? Okay. So also note that obviously capital A subscript capital I capital J of lambda. We're going to do that one next. Adds lambda times. Oh, it's not letting me, right? Okay. Adds lambda times row capital I to row capital J, right? That's just what the elementary row operation does, and we've already spoken about showing that for some arbitrary. Well, I should really say multiplied by the matrix capital A, as lambda times the row capital I to row capital J, in some matrix, in some m by m matrix capital A, right? So we know this is true, right? This is what we've been discussing. So now let's call capital A subscript capital I capital J of lambda multiplied by A, some new matrix capital B, right? So now let's just title that capital B, right? And then we can consider from that capital A subscript capital I capital J of minus lambda multiplied by B, right? And what is this doing? Well, it's just subtracting. Effectively, subtracting lambda times row I from row j. We just added lambda times row I to row j, and now we're subtracting lambda times row I from row j, right? So we just added this. We added some constant value. Now we're subtracting it. So we're just giving ourselves the same thing, right? So intuitively, this is going to give you A again, okay? Because what you have is you have a new matrix, which is just an A, where you've added lambda times row I to row j, and now you've applied an elementary row operation to that matrix, but you just multiplied effectively. Well, sorry, you've subtracted lambda times row I from row j. So you've added lambda times row I to row j, and then you're subtracting lambda times row I from row j. And that's just going to give you nothing. You're going to give you what you started off with again, right? So there's no change in the matrix A when we do this, right? So in other words, what this is doing is just subtracting, right? Because we're adding minus lambda times I, which is the same as subtracting lambda times I, or row I. So in this case, we're subtracting lambda times row I, subtracting lambda times row I from row j, right? Okay, and clearly that gives us A again, right? Clearly, this gives us matrix capital A again, right? Since all we did is we just added and subtracted some constant value to each element in row j. Okay, that's literally all we're doing here, right? We added lambda times row I to row j, and now we subtracted lambda times row I to row j, right? Obviously, whatever's in row I is irrelevant. We're just adding we're scaling each of the elements in row I by some lambda, right? And then we're adding that to row j, but then we're just subtracting the same value, right, from each component, right? Obviously, the value that you're subtracting will be different for each component, but ultimately, it will bring you back to a net change of 0 for each individual component. So you just get the matrix you started off with right back. Okay, so clearly, thus, okay, it's pretty obvious that Aij of minus lambda multiplied by matrix B just gives you A, which therefore implies that Aij of minus lambda multiplied by Aij of lambda multiplied by A, since B is just this, right? We defined B to be this, right? Is equal to the identity matrix about A, which is just A. Okay? So, and it follows naturally that the Aij of minus lambda multiplied by Aij of lambda is just the identity matrix. And the other way around, obviously, you could start by subtracting lambda times row I from row j and adding it back. And so obviously that gives you the property we need to show rigorously that it's the inverse. But obviously it follows, right? And it follows that effectively the inverse, so Aij of lambda, the inverse of that matrix is actually just Aij of minus lambda. Okay, so we've shown that's invertible by specifically finding its inverse, which is not too hard to find because we know what it's doing, so you just reverse it. Okay, and in the third and final case, we have the matrix that basically scales some row up by lambda. Okay, so that's mi of lambda. Okay, now, so finally, lastly, consider, capital Mi of lambda, okay, multiplied by capital A, which multiplies, so what is it doing? Well, we've already spoken about this. It multiplies row capital I, in m by n matrix capital A, right, by lambda, okay? And we're going to do the same trick we've been doing the entire time. call I of lambda multiplied by the matrix A, call it a matrix some matrix B, okay? Okay, so that effectively, well, we can immediately see that mi of lambda to the power of -1 multiplied by b just gives you a. Okay, now let's think about why this is. So all we've done, we've multiplied row I in matrix A by lambda. Then if we just multiply the same row by 1 over lambda, you have a net change of 0, right? You've multiplied it by lambda and then divided it by lambda. You've done nothing. Okay, so effectively it's the same thing. When you multiply something, when you multiply like both sides of an equation by 1, you're not doing anything, right? In the same case, you're multiplying some by some scalar lambda, then dividing by it later on, right? And so effectively, you're just going to get back to the matrix you started off with, which is capital A. Okay, so clearly, multiplying row I by lambda to the -1 is the same as multiplying row I by 1 over lambda. That's what lambda to the -1 is, fairly real number lambda, right? Which is what we have. Not obviously non-zero, not defined for 0, but we don't care because lambda cannot be 0 anyway. Okay, so multiplying row I by lambda to the -1 is the same as multiplying row I by 1 over lambda, which is the same as dividing row I by lambda. Okay, so clearly that's going to give us back to when you multiply row I by lambda and then divide it by lambda, you're going to get back to what you started off with, which is just matrix capital A. Okay, and I explain this because we multiplied row capital I by lambda, and then divided it by lambda, to get A back, to get capital A back. Okay, so, well, what do we know? We know that mi of lambda to the -1 multiplied by b is capital A, and that obviously implies, and b we know is m subscript capital I, it's supposed to be a subscript here. So we know that m subscript I of lambda to the -1 multiplied by m subscript I of lambda multiplied by a is equal to the density matrix multiplied by a, which is a. Okay, so you're just going to get a right back. Okay, and so obviously this, so mi of lambda to the -1 multiplied by mi of lambda will just give you the identity matrix right back. Okay, because otherwise you wouldn't be able to get a right back, right? Okay, and so therefore, and obviously the other way around as well, you can divide by lambda then multiply by lambda, and effectively it naturally follows that therefore we know what the inverse of mi of lambda is, and that matrix is also invertible. So let me just put that in a box. Okay. So, right, so we know that effectively mi of lambda to the power of -1, the inverse of that matrix is just, in fact, mi of lambda to the -1. Okay? Well, that follows. That follows, okay? We haven't necessarily explicitly shown it, but it's pretty obvious, and it can obviously just be, I mean, it's pretty much shown, right? Because we know that the mi of lambda to the -1 multiplied by mi of lambda just gives you the density matrix and the other way around, so pretty much given it to us. Well, we could be a little bit more specific about showing that, right? But effectively, we have the idea. The intuition is 100% there, right? Clearly, when the inverse matrix, right, it's effectively just representing, in this scenario, dividing by lambda, right? Because all we're doing is multiplying row I by lambda and dividing it by lambda, right, to get back to what we started off with, right? And so, yeah, that's pretty much that, right? And so effectively, the inverse of multiplying, some row by lambda is effectively dividing it by lambda, and that's what this is saying. But also with the associated matrices, right? The inverse matrix of mi of lambda is just mi of lambda to the -1. Okay. There we go. Okay. Right. So now here we go. So we have a final corollary that we need to talk about before we finish. Right. So corollary. Now we can finally show what we've been wanting to show for this entire video. So now let's write it out. Let effectively A. So this is just an augmented matrix here. So A is effectively just a matrix of coefficients with a vertical line, and B is basically just the what you have after the equal sign in your linear system, right? So for example, if I have something like 4x plus 3y is equal to 2, 2x plus 5y is equal to 7, right? Then in augmented matrix form, our capital A would be 4, 3, 2, 5 with a vertical line and then 2, 7, right? So that's just the notation that this is basically representing up here. Okay, so then we're going to let that be a linear system, right? Because that also that's a way to describe linear system using augmented matrix. We already discussed that a few videos ago. So let this be a linear system of effectively m equations. Okay, m is just some arbitrary natural number. And we're going to also introduce capital E to be an elementary matrix, an elementary m by m matrix, right? It always has to be m by m. Also, because in this case, obviously, A is going to be some m by n matrix, right? Because effectively there's m equations, so you're going to have m different rows. Okay, so because m by m, the elementary matrix has to be m by m, right? By the discussion we had before earlier on in the video. Okay, so that's that. Okay, then, right, the thing we need to prove is that X is a solution of this linear system, okay? If and only if, okay, if and only if X is a solution of the linear system, but effectively where you pre-multiplied matrix A and effectively matrix B, which is basically column vector, by, any elementary matrix capital E, okay? So effectively what this is saying is that effectively my solutions stay the same, right, when effectively I transform my augmented matrix via some elementary operation, which is the whole point of this video, right? We have to show this, okay? We have to show that effectively by multiplying, in fact, by changing my augmented matrix, by applying an elementary operation to my augmented matrix, which will also apply an elementary operation to the stuff that's on the right hand side of the vertical line, so the b's, all the stuff that's in the column vector b, okay, after the equal sign. Okay, so if we apply an elementary matrix to the entire system, if we apply an elementary matrix to the entire system, but also if we apply a row operation to the augmented matrix, okay, then we're keeping the solutions the same. Okay. That's it. Okay, so effectively, if I have a solution of my system, that will also be a solution of the system where my elementary row operations have been applied. And if I have a system of my elementary row operation system, then that also has to be a solution of my initial system, which effectively gives me that effectively I'm preserving the solutions effectively. Okay, so effectively what that's telling me is that if I don't have a solution, right, to my initial system, I'm not introducing any solutions. I also don't have that same solution, right, to my augmented system with the elementary row operation applied. Okay, so any solution that wasn't already there is not going to be introduced by me applying my elementary row operation. Okay, so effectively we call this the invariance of the solution set or solution space under the effective application of elementary row operations. Okay, so let's get straight into this proof. Okay, so this is quite a short proof, to be honest, because most of it we've already done. So the elementary matrices are invertible. That's the first thing that you need to note. Okay, and it's a key property that we needed to talk about this. Okay, well, to prove this. Okay, so that's good. We have that the elementary matrices are invertible. If matrix A multiplied by our solution, effectively x, which is going to be obviously a vector of solutions, right? We already spoke about this in previous videos. But if you have matrix A multiplied by some vector x, right, which gives you column vector b, right? So if this is true, well then obviously you can just pre-multiply both sides by the elementary matrix E. We didn't even necessarily need the invertibility to do this, right? So sorry, this is equals. We didn't need the invertibility to do this at all, right? This was something we could have done, after talking about really pre-multiplication, to be honest with you. But we wouldn't have been able to do the entire proof. So it's we needed the invertibility of elementary matrices. So obviously this follows by pre-multiplying by E. By pre-multiplying by matrix capital E, right? So what this is saying is if I have a solution, if my column vector x is a sort of vector of solutions to my initial system, then obviously my transform system will have the same solutions. Okay, so that's good. Now we need to show that if my transform system has some solution, has some vector of solutions, and so will my initial system. Okay, and that's when we need to use the invertibility. Hold on here. Okay, if so I should really say likewise, right? If we have a transform solution and x is a vector of solutions to that system, right? Transform system. So this is true, okay, for some, for our solutions, effectively, if our column vector x is some vector of solutions to the system, then it also obviously follows, right, that ax equals b, right? And this is very simple now that we know that that elementary matrices are invertible, because we just pre-multiply both sides by e to the power of -1, because we know that all elementary matrices are invertible, so we'll always be able to do that, right? So by pre-multiplying, right, by e to the -1, okay? So obviously, and that's because if you have EAX is equal to EB, and I pre-multiply both sides by e to the -1, I'm going to have something that is like this. And e to the -1 e, by definition, just the inverse in general, is going to give you the identity matrix I. Okay, on both sides, so you're going to just get IAX is equal to IB. And obviously, identity matrix multiplied by anything just gives you that thing right back. So you're just going to have IAX is equal to B, which is exactly what we want. Okay, so evidently, if and that obviously critically hasn't changed the vector x, which is our solution vector, basically, right? So ultimately, it hasn't changed the solutions to our system. Okay. Right. So there we go. That is that proof, and that's pretty much the video. But let me just also finish this up by saying that this shows, right, that applying an elementary row operation, or even any succession of EROs, because you can just keep doing this over and over, right? Actually, that won't alter the solution space. It won't alter the set of solutions of a linear system. Okay, so that's sort of a more rigorous pathway to that result. Okay, and so that's pretty much it for the video. In the next video, we're going to talk about reduced per echelon forms. We're going to actually talk about what this chapter is named, and then we'll effectively aim to show that we can always reduce a linear system to reduced per echelon form, right? And we will prove that. We can effectively just read off the solutions, or read off if there's 0 solutions, infinite many solutions, so on and so forth. Okay, so we'll prove that you can always get to that point from any linear system, like from any starting point. Okay, by some application of EROs. Okay, we'll discuss it in the next video, but for now, thank you guys very much. If you've watched the entire video to get to this point, thank you very much. It's been quite dense and in some quite tricky theory actually. So yeah, thank you very much for watching. Have a good rest of your day, wherever you are, and I'll see you guys in the next one. Goodbye.